Hello everyone. If you remember in the first video about template matching, I mentioned that template matching using methods like normalized cross correlation or sum squared differences normalized, that is limited in what it can do. It can only find the template in the source image if the template is just displaced or translated. If you have rotations, if you have skew, if you have a scaling or anything, you cannot find the template. And so this brings us to this current video where the goal here is to find some features or feature points that are robust to these other transformations. So if the template is rotated now or scaled or moved, I still can find it in the other image. So I need some feature points that have robustness to all of these transformations. And the first one probably is the SIFT method, which is a scale invariant feature transform, and SIFT had the property that it was robust to scaling, as well as, of course, translation. And it wasn't the best when it came to rotation and skew and some elimination changes. And SIFT was patented until a couple of years ago. And so many of the major software, including OpenCV, which is a bunch of libraries basically, or MATLAB or anything, they did not really had SIFT. And it's interesting that after version 3.4.2 of OpenCV, still they decided to not use SIFT. So if you look for SIFT, you cannot find it in OpenCV, and then it's not really the best because it's quite a bit slow. And then other methods came like surf, right? Speeded up robust features, and then fast and brief and so on. And in each iteration, these methods got faster and faster. Surf was multiple times faster than SIFT. Fast was even faster, and brief. And now these two are almost real time, and they can be very good. The problem is all of these guys are patented. And so if you want to use the free OpenCV, you cannot use these. You have to pay a few dollars each month. And so OpenCV came up with the ORB method, which is the oriented fast and rotated brief. It's a mixture of those two. And this method that the OpenCV libraries came up with is a very good method, very fast, very reliable, and it is free. So that's why here I have choose the ORB method, because I can apply it without paying for it. So what I have here, I brought in two images and I read them in grayscale. Remember, when you read an image with IMRead, if you pass 0, you can bring it grayscale. If you pass 1, you can bring it in color. Another way, instead of saying 0, you can say cv2.imread_grayscale. That's the same as saying 0. Okay, so I'm bringing two images in grayscale, no color, and they are the Lena image and then the transform version of the Lena, which is smaller and also rotated. Okay, and I want to find the feature points common to both and show you that the matching is really very good. And then I find a homography based on these two and apply it to another image, OpenCV, and give you a new image. So let's go through all of this. The first thing you need to do is you create an object for the ORB. So you say CV2 ORB create, that creates an ORB basically object, and then this ORB has a detect method, and it also has a compute method, and it has a combination called detect and compute, where not only it detects those feature points, it also computes the descriptors of each feature point, and it returns to you the points as well as the descriptors, okay? And the first item that you pass to it, input, is the image, and the second one is the mask. So if you just want to find the feature points for a portion of the image, not the whole thing, you can pass a mask here. I don't have, I want it for the whole image, so I say none. And then you can pass those points and the image to the function draw key points. And this guy is going to take your image, it's going to get your points. You can provide an output image here, or you can apply it to the left-hand side using equal sign. If you provide it here, then you don't need to assign it to anything. Here I say none. Instead, I provide the output image on this side, And then what color do you want to use? So here I'm using green, and then I have a flag of 0, right? If you want, I can describe what that flag does for you. So you can pass to it different numbers for the flag, and this is for drawing. So there is a default, there is draw over out image, not draw single points, draw rich key points. So depending on which flag you pass, it is going to draw those feature points in a different way, right? So it is going to draw all feature points the same size, whether they are strong feature points or smaller or not strong feature points, or you might call them rich and not rich feature points. If you use this last one, which is flag 3, this default is flag 0. This last one, which is flag 3, this guy is gonna show them with size. So the bigger ones are the ones that are basically stronger feature points. It also shows the orientation for them and so on. Okay, so if you want, you can read over this page and it tells you exactly, or we can experiment with them. We can pass 0, 1, 2, or 3 and see how it is gonna show the feature points for you, right? So right now I go with the default 0, but I can change it. And then once it overlays all of those feature points in green over my image 1 and call it image 11, I'm going to show you image 11, which is for the image Lena, and then I do a similar thing on the transform version of the image Lena. Okay, so before I do anything else, let me run the code up to this point so we can see how these points are detected and shown on the two images. So here is image Lena, here is the transform image, which is rotated and scaled down. And you clearly can see, if you look at these points in green, these are the dominant feature points or feature points. And if you see them in both images, it kind of detected the same locations, right? Mostly. Not all of them are perfect match, but a lot of them around the eyes, in this area of the hair, these areas on the hat and so on, around the shoulders. You see that most of them are similar, and then it is going to match the ones that are having similar descriptors. Okay, so you see these feature points are quite a bit robust to rotation, scaling. Definitely there is translation here too, right? But even if there is not, or there is, it's not going to affect any of the performance here. So now that we have detected the features, it is time to match the features and see which one of these in the image 1 are corresponding to which ones in image 2. And here you need to use a feature matcher, and one of them is the BF feature matcher or brute force. There are other feature matchers too, and brute force is one of the simple ones, so we're going to use CV2 BF matcher. And what you need to pass to it is here I'm creating the object. So to create the object, you have to say which norm to use and whether you want the cross check or not. And the norms, there are different types of norms that you can use. So if you are using SIFT and SURF, the norm to use is the L2 norm or Euclidean norm. But for methods like ORB, brief, brisk, and so on, that are using binary string-based descriptors, you better use the Hamming norm, not the what, not the L2 norm. Okay, so here we are using the Hamming norm, and then we pass to it the descriptors of image 1 and image 2 and say bf.match. So we use the match method from this object bf, and it gives us all of the matches. And then we are going to sort these matches based on what? Based on the distance. Okay, and here you see I'm using a anonymous function, a lambda function here, and I say use this lambda function, which is the distance between them, and distance here is determined by the Hamming norm, and sort them based on that. So the points that have smaller distances, the descriptors that are closer to each other, sort them on the top of the matches. The ones that are what? Having larger distances, bring them below, bring them down in the matches, so give them lower priority. And then here, I use this command draw match, which you pass to it image 1 points 1, image 2 points 2, and then from these matches you only care, let's say, keep the top 10. Okay, so here you're only keeping the top 10 matches. And then you're going to say what? Go ahead and again here, this none is the output image. You can provide it here or provide it on the left side here. I keep it on the left side. And then you have another flag for showing basically the feature points on the two images. So this flag, you can change it again, right? 0, 1, 2, and the way that it is going to show the two feature points and the way that they are matched, this is going to be different, right? So here, if we go with flag number 2, okay, and creates image 3, which puts the two images next to each other and shows the key points on them, but only the key points that are the top ones. And with arrows, it is gonna connect them together, right? So let me go ahead and show that to you here. So this is what I said. And here, although I asked for top 10, it did not even find 10 for me. As you can see, it only found 7 of them for me that are matching very strongly. So there are tons of points, but this method only used the top 7 ones. And you clearly can see that these points are exactly referring to the same physical points, right? If you look at them, right, this point in the hair, that point in the eye, this point on the head, these 2 points on the hat, these 2 points on the shoulder, they are being very what? Very physically accurate. So clearly this method is working and the matching is working. As I said, this is not the only matcher. There are other matchers too, but this is one we're going to use today. And so you see now that the matching is happening, now we can calculate the transformation that takes you from one image to the other image, and that is what we call a homography. So what is a homography? Homography is a 3 by 3 transformation matrix that it takes you from one image, any point from one image, and send you to the point, the corresponding point in the other image, right? And if you want to determine the homography, you need at least 4 pairs of correct matches, a minimum, to calculate the homography. At least 4, and here we had 7, so we should be good to calculate that homography. Now, the most important thing about homography is it's the picture of the objects on the same plane that you take in the real world when you move camera from one position to the other. So the scene is planar. Your points are almost on a plane, and you take a shot from that scene from one angle, and then you take a shot from that scene from another angle and another distance. So the rotation happens, the scaling happens, the translation happens. And then as long as those points in the real world, they are on a flat plane, then you can relate their projections in the two images using this 3 by 3 matrix that we call homography. Now, question is, in the case of this Lena image, are those points on a plane? And the answer is not exactly, because some of them are on the shoulder, some of them on the head, hair, the other one on the hat. So they are not perfectly on the same planar surface. But if you assume that the distance from the camera to the face is quite bigger than the thickness of the elements in the image, which is thickness of the body parts or the hat or something, then you can roughly approximate those points as belonging or being on the same plane. So this is not the best case of a homography. This is just a rough approximation because the planar case is not exactly there. But it's relatively good. So here, what I do is, for the homography, I basically create this PF object, which I already have, and seems like I have copied a code twice, seems like, again, except for this D matches. So let me get rid of that, although this D matches and the matches are the same thing here. So let me get rid of this part of the code, which I have copied twice. So this D matches is the same as the matches here. And what I do is here I'm converting my points, my feature points that you see by KP1 PT M query index for M in the matches. So you go over each and every one of the points in the matches, find the corresponding points in the set of feature points, and you are going to convert them into float, and you are going to reshape them -1, 1, and 2. You might say, what is this guy? What this one does is what we call opposite of squeezing. I had a video on linear algebra using NumPy, and I talked about the squeezing, removing the dimensions that have 1 in them, right? So convert a 4 by 1 by 3 vector into a 4 by 3 and get rid of that dimension of 1. Here you are doing the exact opposite. If you pass 4 and 3 to it, it makes it 4, 1, and 3 or something like that. So it's a de-squeezing basically that you're doing, and the reason is these source points and these distant points that your find homography command needs have to be in such format, okay? You'd expect them to have an extra 1, and that is because they are in the homogeneous coordinates. So here you're adding the extra 1 here, and you're converting them into float numbers because they are not float numbers. And then you pass these source and destination points, okay? The points in the image 1 and image 2, the ones that are in the match among those 7 sets of points, or 4, or whatever it is. Pass them to the command find homography. And this is going to estimate for you the 3 by 3 matrix. And the other thing that you need to do is use here the RANSAC method to estimate the parameters, those numbers in the H matrix, with robustness if there is outliers in them. Now, in our case, we didn't really have outliers. The 7 matches were really good and perfectly good, but not always the matches that you find from this brute force or any other matcher, they are not always perfectly good. Sometimes they have offsets and so on. So one point is, let's say, on the left eye and in one image, but you see the corresponding point that it finds in the other image is kind of like on the right eye instead of left eye. So those are outliers, and when those guys exist, the estimate for the parameters in the H matrix are not going to be so good. They are like outliers. And the RANSAC method, which is random sample consensus, this is a method, it needs a lecture of its own. I'm not going to go over the details of that, but this is a method for estimating the parameters of a model if outliers exist. So you use this method to help you get better estimates, and this 5 is one of the thresholds called reprojection threshold for the RANSAC that you have to use in that parameter, and in our case it turned out 5 is a good number. So you calculate the homography, and once you calculate the homography, now you can apply it to any other image. Like in my case, I'm going to apply it to the OpenCV image and warp that image to get image number 4. So what am I doing here? Whatever relation exists between Lena and transform Lena, which was a rotation, right, and scaling, I am going to apply it between what? Between the OpenCV image and this new image, image 4. So I expect image 4 to be smaller and a rotated version of the OpenCV image, okay? And for that, I'm going to show you both the original image and the homography warped version of the image. And the command to do the warping is called CV2 warp perspective. So you apply a perspective projection, which is done using a homography matrix. So you pass to it the original image, you pass to it the homography, and you pass to it the size of the output image. And that is going to give you the output image. So let's go ahead and run it, see what it gives us. And if you can see here that This is the image Lena and the transform version, which you see the rotation and the scaling. And if you look here between OpenCV and this, you see that the image is made smaller as well. What? It is rotated almost the same angle as this one is rotated, right? So you see that this warping is working, and this is one of the things that you can do when you calculate the homography. You can apply that relation, that homography, to any other sets of images. And one of the major applications of homography, by the way, if you're wondering where is this homography used, is creating panoramas. So you go around the scene that is almost planar, and you take so many images, and then you can transform these images back to the same base and stitch them together and make a panorama. And that's something that your phone also does when it gives you that panoramic image. That is what your cell phone also doing, calculating homography and a bunch of these tasks. So hopefully this video was useful to you. You learned how to detect and match ORB feature points, and then how to use RANSAC to calculate the homography, and how to use the homography to warp an image into another one, and some applications for it. Thank you so much. I'll see you in my next video.